found D. This is the normal way. And we found D was Q over 4 pi R squared AR. Everybody understand that? Now, after you get D, you find E. And E is equal to D over epsilon. And this is real important. Now, if epsilon is a function of position, then it may change. Instead of varying as 1 over R squared, it may vary as 1 over R cubed or 1 over R. Follow me? If epsilon is a function of radial distance, it will augment the actual signature, or how the E field changes with distance R will change from how the D field does. So in our case, if E is a constant, if epsilon is a constant, it will be just Q over 4 pi R squared epsilon. And if it's a constant, just be epsilon between the plates and would be in the AR direction. Do you all see what I'm talking about? Now, the next step would be we get V. And V is always going to be the integral of E dot dl. So to get V, we take the integral of E dot dl, and you only worry about the positive value. If you get a negative, you forget about the negative sign, because the truth is, when we talk about capacitance, we take the total charge divided by the total voltage, both of which are positive, assume positive. Capacitance will always be positive, not negative. And we can just go from A to B and do an absolute value here to get rid of that. So now we're going to take the integral from A to B of this, which is Q over 4 pi epsilon, right there, times R squared AR dot DL. In our case, it'll only be DR AR. And when you do that integration, you'll find it's what? Q over 4 pi epsilon is out in front. And when I integrate, the AR dot AR is 1. When I integrate 1 over R squared, I get minus 1 over R, correct, class? And minus 1 over R, if we take it and put in the boundaries, will give us a magnitude of 1 over A divided by 1 over B. And that would be the voltage between A and B, positive voltage. Do you all see that? Now we get the capacitance. And capacitance would be Q over V. So I take Q and I divide it by this V, which is Q over 4 pi epsilon naught, or 4 pi epsilon, times 1 over A minus 1 over B. I did this last time, but I'm doing it again for a reason. You can see the Q's cancel. Capacitance will not be a function of charge unless it's nonlinear. The 4 pi comes upstairs, and I have 4 pi epsilon divided by 1 over A minus 1 over B. Last time I said sometimes people just put A minus B or something like that, and I never have understand how they can justify that, but in their minds, they miss something. Now that's the capacitance if the epsilon value was constant, correct, class? And I assume Q, I got D, got E, then got V, and then I did Q over V to get C. And that's the way they did it in physics back in the day when you had physics. This is a very classic problem. Now, what happens if epsilon isn't a constant? Which is a good question. Suppose now I let epsilon between the plates be equal to like epsilon naught divided by R. All right, still spherical, inner radius A, outer radius B. But now my epsilon's a function of R, right? These aren't great drawings, but I hope you appreciate what I'm doing. And now I want the capacitance between the inner and outer plate. Let me just make a side note on this one. Somebody's going to say, well, how can you even charge this capacitor if you can't get to the inner plate? The truth is, with a spherical capacitor, they'll bore a small little hole here, and they'll put a very thin wire with insulation around it and connect it to that ball. All right? And then they can put charge on, and it's not a problem. And they'll ground the outer surface usually. That's the real way that they do this when they create spherical capacitors. So next, when I take a look at this thing, I'm going to go ahead and calculate the capacitance of this. Here, epsilon is not a constant, so follow me. First thing is I assume Q, right? Whatever it is, it's going to cancel anyway. Then I get the D field. D field's the same, right? D field isn't a function of epsilon. It's just Q over 4 pi R squared AR. Everybody agree with that? But what changes now? When I get E, that's my next step. What happens? I get D divided by epsilon, and now I got Q over 4 pi R squared. But what is epsilon? It's epsilon naught over R, right? AR. You see what happens here? The R squared divided by R gives me just a 1 over R term. So now this becomes what? Q over 4 pi R, or 4 pi epsilon naught R, AR. Agreed? It's not changing as 1 over R squared. Everybody follow me on this, guys? And if I'm going too fast, tell me to slow down. You good? All right. So what's the voltage now? Remember, I only want positive values between the inner and outer plate, between, say, B and A or A and B. Well, be the integral of E dot dl, or Q over 4 pi epsilon naught R AR dot dr AR, right? And it goes, in this case, from A to B. And what's that going to be? Well, AR dot AR is 1. Then I get Q over 4 pi epsilon naught. And what's the integral of 1 over R? Anyone?
Natural log.
Natural log. And now you evaluate between B and A. And finally, what's the capacitance going to be between the inner and outer radius? Well, it's Q, right, over VBA, or the Q's cancel, and that means I get what? 4 pi epsilon naught divided by the natural log of B over A. Take a careful look at that. Do y'all agree with that? Class? Y'all see what I've done, Tyler? What? Oh, yeah. I just said that what I'm doing is just taking Q, the assumed Q, and dividing it by VBA, which really gets rid of the Q and just takes 1 over what's left. So I get 4 pi epsilon naught divided by natural log of B over A. Here's something to note too here. Capacitance will always be a function of epsilon. Epsilon will always appear to be multiplying some scale factor. So you see epsilon naught here appears here, right? Capacitance will always have epsilon up top. Now, the larger the value of epsilon, the larger the capacitance. It's always going to be that way for a given geometry. Keep that in mind. Epsilon is proportional to capacitance. Let's do another one. And this time, I want you to work with this. You work this one with me. This is going to be a cylindrical system, and I want the capacitance per unit meter of this. So I'm going to have an inner radius of A. This is a conductor. Then I'm going to have an outer radius of B. And these are just conductors. Goes on forever, assume that. And I want the capacitance per unit meter of this system. So I want the capacitance per meter. So how do you do that? What are you going to do? Ron, well, go ahead.
Assume a charge Q.
All right, and it's per meter. Remember this. We're going to assume a Q per meter. We're just assuming this. So if we take a meter long section, we assume it over that meter long section, it has a charge Q. Are you with me? It effectively, this is like rho L, isn't it? The charge per unit meter is like rho L. And here's the neat thing about this. Now, actually, the charge is uniformly distributed over the surface of that inner conductor, right? But if you want to put it all down to a line charge, it will give you the same result. And the reason is when we use Gauss's law, if we are between R greater than A, less than B, and we do the integral of d dot ds, that will be the integral of, in this case, rho s vs, or it will be simply Q per meter. And if you do a 1 meter section, it's just going to be Q. Well, D dot ds, this is assuming it's an infinitely long cylinder, and therefore the D field has to be in the radial direction or the rho direction because of symmetry. Do you all agree with me? If you have an infinite cylinder, the D field is going to be radially outward. And this will just be 2 pi rho times d rho. We're assuming that the height of this thing is 1, will be equal to the charge per unit meter, just Q in this case. So we have d rho is just Q over 2 pi rho a rho. Everybody agree with that? Guys, this is just like a line charge, right? What's my next step, anyone? What about Haran? Can you hear me okay? What's the next step? You're going to have to unmute your mic. You're still not unmuted. There you go. All right. What would E be? You're right.
Just D over
Epsilon. So it'd be Q over 2 pi epsilon, whatever epsilon is, rho, a rho, right?
Yeah.
All right. What's the next step? You want to keep going with this? Think about it. If we got E, what's the next thing we need? We're almost there. We need V, don't we?
Oh, yeah.
All right, so how do we get V? The integral of E, right?
E times DL.
E dot DL, and we integrate it, right?
Yeah.
And we'd integrate from A to B. And we just get rid of the negative sign if it turns negative. So this is going to be equal to what? The integral of Q over 2 pi epsilon, I'm just going to call it epsilon, sorry, rho, right? A rho dot d rho a rho from A to B. And what does that give us? Go ahead. Well, I have Q, right? And I'm going to have Q, and then I'm going to have 2 pi epsilon. Epsilon's a constant in this one, times, well, a rho dot a rho is 1. What's the integral of 1 over rho, class? Or
Log.
Just natural log, right? Natural log of B over A. And finally, what's the capacitance? Do you want to tell me?
It's Q over V.
Right. I know it's early, but interaction is helpful. And I don't mean to irritate people. I'm not trying to call on people to bother them, just so we can get some interaction. It'll make this stuff stick with you better. So you end up getting what? This is going to be 2 pi epsilon naught over the natural log of B over A. Everybody agree with that? Class, you guys okay with that? Now, you notice it's the same basic form as the last one, only in the last problem we had 4 pi epsilon naught, right? Over the natural log. Here we have 2 pi. Agreed, class? But that's correct for a cylindrical system. Now, if I put that make that dielectric a function of position, then things change. Because then if I made it, for instance here, if I made epsilon right here, epsilon naught over rho, the rho's would cancel. Do you all see that? And then if the rho's cancel, what happens? Then when you're integrating a constant d rho, just get rho, agree? And it would be evaluated between B and A. So you have to understand that those kind of things can happen, and because the problems we create are basically abstract, just to make sure you can do your math. The final structure, the common one, is yeah.
Before we go on, I was just making sure on that last problem for capacitance, you did end up, it's not, you're just using epsilon naught, right? It is like epsilon,
yeah,
correct?
I'm
because epsilon constant.
I'm assuming epsilon is a constant. It's really epsilon relative times epsilon naught, but I'm not having it vary spatially.
Okay, that's what I thought. I was just making sure.
All right. Everybody good? All right, now this is the one that, this is the planar structures, or the one set of structures that you assume a voltage first. And let me show you, this is going to be a parallel plate capacitor. So when you have a parallel plate capacitor, you have to make some assumptions. And we're going to have one surface there. Here's a second surface. They're going to be spaced by a distance d. This is going to have a surface A. The area of the plate would be A. But we assume d is much, much less than the square root of A. This is the only way this is going to work. Now, here's what it really is saying. It's saying that these plates are going to be very close together. So if you take a look at the length of an edge on this plate, compared to D, D is going to be much, much less than the length of the edge. And the length of the edge is proportional to the square root of the area. Because area is length times height, or length times width, right? Class? So this is the assumption. This is the only way that this will work. So if you have that, then what happens is this. If you assume that, and there's a dielectric between there, then we assume V. So we're going to start by assuming V. And V would be a plus to minus voltage between the plates. Y'all see that? Now remember, this is a very thin structure. Give me 1 second. This is from the administration. Actually, the chair of the Senate. Okay. If we assume V, this is the thing you have to understand. Because they're two parallel plates, there's no curvature. It's not like cylindrical surfaces or spherical surfaces. You can get the E field between those plates by saying it's just equal to V divided by the spacing. And think about it. The voltage is in volts, and the electrical pressure is in volts. E field has the units of volts per meter. The E field will not change in magnitude between the plates. It'll have the same magnitude, same direction, if they are truly parallel plates, and it's just V over D. Y'all follow me? Here you could put in an arbitrary direction. I can make that plus, this minus, or vice versa. And I can say this is the Z direction. Now that means the E field is actually minus AZ. Y'all follow me that? And I put my own coordinate systems in. So I said, that's the Z direction going up. Therefore, the E field is pointing in this direction between the plates, down. How many see that? Just so I get an idea. You all see this? And you've seen this in physics too, when your prof did that in physics. Now, the next thing I'm going to get, after I get E, I'm going backwards. Now I get D, all right? And D is epsilon E, right? So now I can say that the D field here would be equal to minus V over D times epsilon, whatever epsilon is. Right? Y'all agree with that? Now, here's the neat thing. These are conducting surfaces. You only need the magnitude of the charge on one of them. And here, right at the surface, the lower surface, the E field's pointing into it, or the D field's pointing into it. And that means we can find rho S, which would be equal to D normal on a conductor surface. I just mentioned that earlier today, didn't I? On a conductor surface. And that means I can say this is rho S. So I can have rho S on a lower plate would just be equal to minus V over D epsilon. You can forget about AZ. And now the total charge Q. Does this make sense what I just showed you right here? I found the D field. That's D is in it's what? D is in coulombs per meter squared. It's the same thing as rho s, coulombs per meter squared. Now I have to find the total charge. So I find the total charge by just integrating rho s over the surface. It's just multiplying by the surface area, the lower surface area here. So that's going to be A would be the surface area times minus V over D epsilon. Y'all follow me on that? I let them in terms of constants. You good, everyone? Finally, for the capacitance, you say capacitance is Q over V, and you take the magnitude. So I lose the negative sign here, and I lose V, and I find out the capacitance of a parallel plate system is epsilon A over D. Y'all see the steps I've done here? Now I'm going to show you a twist on this one. It'll help you. And how many remember that formula for parallel plate capacitance? Capacitance is always proportional to plate area, inversely proportional to distance. Here's the trade-off. Remember I told you about people want supercapacitors? All right, here's the thing. As D gets smaller and smaller, the capacitance gets larger and larger, right? And you're occupying a smaller volume, by the way, aren't you? But look what happens to the E field. The E field is going to be whatever the voltage is divided by D. Well, as D gets smaller and smaller, the E field between this is getting up, right? And the real problem is the breakdown strength of the media you have here is the thing that will limit the value of capacitance. Your value of epsilon is going to be linearly scaling, but if you had something that could withstand like 5 billion volts per meter before breaking down, then you could store a whopping amount of energy in there, regardless of the value of epsilon. But the truth is that it's usually the thing that is the breakdown voltage in the material limits the actual capacitance. Now, for air, like around here, it's about 3 million volts per meter. For mica, it's 200 million volts per meter. And if you think about that, that's a factor of 40 better than air as far as the maximum breakdown voltage. This is capacitance, by the way. Something to note that you learned when you had circuits is that the energy in a capacitor, or they call it W in a capacitor, is 1/2 CV squared. Y'all remember that?
Can you scoot the paper down?
Yeah, thank you, thank you. That the energy in a capacitor, this would be in joules, is 1/2 CV squared. How many remember that? Anybody? Now, the thing about it, it's proportional to V squared. So if you can store a very large voltage on your capacitor, you can get a lot of energy because the energy is going up as V squared. And that means a very large breakdown potential, or the material has to be able to withstand a huge amount of volts per meter before breaking down. I'm giving you just some insight into this. You'd be surprised how small the capacitance value is in most cases. If you get anything near a millifarad with a reasonable breakdown voltage, like a couple hundred volts, it's usually a fairly large capacitor. We had capacitors that I worked with when we built a rail gun, and that's just an electromagnetic gun, basically. We built a rail gun, and we were using, they're filled with a liquid, but they're actually, sorry, this one wasn't. The high energy capacitors are made of it's a type of capacitance known as a, somebody's cutting the lawn next. They're called an electrolytic capacitor. Have you heard of this? Anybody? Electrolytic capacitors? Well, electrolytic capacitors are something that allow a huge amount of energy to be stored, and they have a fair amount of breakdown strength, but they can only be polarized one way. So if you have the plus to minus, you can only put plus minus voltage. If you invert that, they'll blow up. And I guess you probably don't know about this, but back in the day when we had laboratories that were very extensive, we had available to us capacitors, some electrolytic, and you could always blow one of them up if you want to have some fun. sounded like an M80. It's not the wisest thing to do, but I've actually seen the aftermath of a large capacitor where they were discharging it, and unfortunately there was enough inductance in the line that it kept the current going, so it's going to charge the capacitor in the opposite direction. It blew up, and it looked like somebody set a grenade off it. Just it's a lethal thing if you're there and it happens. It may kill you. But those are electrolytic capacitors. The thing is, they can store an enormous amount of energy. But I want to get back to my point. When you get capacitances that you worked with in the lab, they're usually what? Between picofarad and microfarad, right? Maybe 10, 15 microfarad. And they have voltages that they can withstand of a couple hundred volts. Our capacitors that we were using could withstand 10,000 volts. And they were 32 millifarad. Now, if you can do the calculation on that, we had 4 of them that we used in parallel to discharge it. You can see that the amount of joules we're using is hundreds of joules. I'm sorry, tens of thousands of joules, and I believe that's right. But they were massive. Each capacitor is 250 pounds. They were about 3 foot, 2.5 feet tall, and by a foot square, and they were massive. And I'm just giving you a perspective of where we were back then for a capacitor that could store a fair amount of energy. Now, what they need is a capacitor that can store about 100 times as much energy as one of the ones I was using in a volume that would be like this phone. That's where they can get to the point where they can use those as power sources in their in like electric cars and stuff. But right now, the only thing that really stores energy that they can use, I mean, a significant amount of energy for cars or anything like this, are either lead acid batteries or lithium ion batteries. They're chemical batteries that store the energy. But they can get it, you can only get that out very slowly. You can't get it all out in like a second. It takes, I don't know, for a regular chemical battery, I think it takes, even with a dead short, it takes about 15 minutes before it's completely discharged. And if you put a dead short on it, it'll heat up really fast and blow up too on most batteries. So those are some of the considerations. Now I'm going to talk to you about capacitance in terms of how you look at capacitances in series and parallel. And you all remember this from circuits. If I had a C1 here and a C2 here, and I wanted to know what the equivalent capacitance of that was, well, do you remember how to get it? It would be what? It's like resistors in parallel. It's 1 over C1 plus 1 over C2, right? Do you all remember that? Or you could multiply, you could say that C here would be C1 times C2 over C1 plus C2. Either way, that's the equivalent value of these two capacitors in series. How many remember that from circuits? Y'all remember that? Capacitors in series add like resistors in parallel. If you had another one, what would happen? It would be what? Just plus 1 over C3, correct? And then you forget about that. You agree, class? Now, in series, there's one thing for sure, that the current through each one of those capacitors would be the same. Agreed? If they're in series, not the voltage. When you talk about looking at things as a lumped element or a single capacitance, and they have to do with geometric configurations, I'll show you how you think about it. If you have say you have a spherical capacitor, has inner radius A, outer radius B, and B has got a conducting plate on it, and it has some epsilon 1. Now you all agree that we can find out the effective capacitance, I'll call it C1, between A and B. You all see that, class? I'm calling it C1. How many see this, just to make sure? If you got a sphere, right, and it's conducting surface right here at the inner core, and A, then there's an effective capacitance. Now, what if I go ahead and say this has epsilon 1, but outside this conducting surface, and it doesn't even have to be a conducting surface, because this could just be something that's going to be pushed right up against a second dielectric. But if I have, now I go out to C here, and I put a radius there and put some epsilon 2, then this looks like an effective capacitance C2 between B and C. Do you all see that? I want you to take a look. Now, the way you solve a problem like this, you could go ahead and put charge at the center, right? Calculate the D field, and then get the E field by taking the D field and dividing it by epsilon, right? Get the E field, then integrate from here to here. Then you'd have to take the same D field and divide it by epsilon 2 and integrate from here to here. And you'd have to go through several additional steps. But the easy way to do that is just get the capacitance C1, and that would be 4 pi epsilon 1 over 1 over A plus, or I mean minus 1 over B, right? And then get C2, and that would be 4 pi epsilon 2 over 1 over B minus 1 over C. And look at them as if they were in series and add them. Can you all appreciate this, class? Now, how do you know they're in series? Because the same electric flux goes through both of them. Before it was current. But here, you all see that the total amount of D field, or the flux, that penetrates or goes through this first capacitor between the first and second plate must flow between the second capacitor between here and here. You all see this? They're in series. You can think of it this way, that if you draw a straight line from here to here, you have to penetrate from the inner core, from the first plate to the second plate, you have to penetrate both capacitors. They're in series. How many see they're in series there, class? You with me? Now, by the same token, I could come up with a structure like this and assume it's spherical. I could say I got an outer radius B and an inner radius A. But what I can do is say, well, half of this has epsilon 1 and half of this has epsilon 2. You all see what I'm talking about? And I want to ask you about this one. Here I've got something, I've got half of this spherical capacitor with inner radius A, outer radius B has epsilon 1. The other half has epsilon 2. All right. Doesn't it look like there's an effective capacitance here, epsilon 2, and an effective capacitance here? I mean, C2 and C1. Y'all see what I'm doing? And aren't they in parallel because they have the same voltage across them? I'm going to talk about this for a second, and I'm going to redraw it over here. So I'll make it bigger too. This is inner radius A, this is outer radius B, and I'm going to say half of this has epsilon 1, half of this has epsilon 2, and this is a sphere. And I want the capacitance. Any takers on how you do it?
If they're in parallel, do you just add the two?
Yeah,
Like
but
half?
let me ask you this, Tyler. How would you get this capacitance in this region? You're absolutely right. There's two effective capacitors in parallel that we would just add. Now we need to get the values of those. All right, let me ask you this. Suppose the whole thing had epsilon 1 in it. What would C1 be? It would be 4 pi epsilon 1 over 1 over A minus 1 over B, correct? But it doesn't have a full surface, right? It has only one half of the area of the plate. So if I divide this by 2, doesn't it make sense that would be the capacitance of C1? By the way, if the surface area of C1 was only 1/4 the surface area of a complete sphere, then you would divide it by 4. But it's divided by 2 here because it's exactly half of the place has epsilon 1, half of epsilon 2. All right, what is C2 going to be? Well, it's 4 pi epsilon 2, 1 over A minus 1 over B, right? Times 1/2. Do you agree? When you add the two together, C total being C1 plus C2, what do you end up getting? Well, you get 4 pi, right, over 1 over A minus 1 over B. And then it's divided by 2, and it's just epsilon 1 plus epsilon 2. Do y'all agree with that? Now, that's if it just hang on for 1 second. I got to take this. Hello? I don't know if you guys get this. I just got an urgent message for the vehicle owner. It's out of warranty. Trying to sell me something. I regret that they have my phone number. Y'all with me on this class? And so it could be parallel or series. Just remember what I'm showing you. If you can see how you can partition into either a parallel or a series region and calculate just that capacitance, then you can add them accordingly. If they're in series, it's 1 over C1 plus 1 over C2. If they're in parallel, it's just C1 plus C2. Follow me? How many understand that principle, class? Just make sure I understand that you do. Got it? All right. Now, the last thing we're doing in this chapter is going to be something called boundary value problems. This is down here if you have your book. And when you're dealing with boundary value problems, you're solving a differential equation. And I'm going to show you where it's in the book, and I'm going to show you the easy way to think about this. If I can find it. It's in Whitworth's book on page 190. But I'm going to show you the way you do it, or the way you should think about it. When you have a boundary value problem, almost always you're solving for the potential between some plates, some types of plates. So if we start with a boundary value problem, let me do the, I'll do the classic one, parallel plate. I'll start here. So if I have a parallel plate capacity, this isn't a very interesting one, but it serves the purposes. And I have the plate area A here, and I have a spacing D, and I have epsilon here between them. Well, we know a couple of things. First, we know that between the plates, so this is between the plates, that rho V is 0. Do you agree with that? On the plates, there is some charge, but between them, you assume it's charge-free. It just has a value of epsilon. Now, then we go ahead and we say, well, I know the divergence of D is equal to rho V. It would be equal to 0, right? And I know D is equal to epsilon E. So I know divergence of epsilon times E is 0. Now, here's where an assumption's made. If epsilon is constant, it can't be a function of position. If it is constant, then we can say that the epsilon comes outside and we can divide by it. And now we have divergence of E is equal to 0 as well. Do you agree with that? And then we can say that, well, we know E is minus the gradient of the voltage. Do y'all remember that for electrostatics, right? E is minus the gradient of the voltage. Do y'all remember this, class? How many do? I want to make sure I'm getting through you. You guys got it? So you plug this in here, and now you get something. You get minus grad V, and then you have to take the dot product of it. Well, that ends up with something called the Laplacian. It'd be minus del squared of V equals 0, and you can get rid of the negative. So we get something called del squared of V equals 0. This is the Laplacian. And in your book, it's in the back of the book too, but del squared operation is a double derivative of the voltage with respect to x, second derivative of voltage with respect to y, and second derivative of voltage with respect to z, and it's a scalar, not a vector. Now that's in Cartesians. In cylindrical coordinates, it's this. And in spherical coordinates is this. Now this looks daunting in some ways, because you're going to be solving this. But the real truth is this. When we have a parallel plate capacitor like this, you can say this is going to be x, and this is going to be y, and this is z. All right? Y'all follow me? I'm just putting in arbitrary coordinates. Now the plates are in the xy planes, right? At constant z. And when you look here, you assume you can, for this, to make it, to just talk about a realistic approach to this, you can assume that these plates are about infinite in extent. And if they're infinite in extent, then what we can say is that the derivative of the voltage with respect to x is really zero. It doesn't change. Just think about this. If I'm moving across this plate, isn't the voltage the same all across the plate if we charge it up, right? If it's a conductor? And it's the same if we go in the x or y direction. But the voltage only changes as I go from one plate towards the next. Do you all see that? So the change of voltage with respect to x will be zero, and that means the second derivative is zero. And the change in voltage with respect to y is zero. Only the change in voltage with respect to z will be non-zero. So I'm making my case. I hope you guys appreciate this. So now I can come down and say for the planar case that I'm talking about here, the del squared of v will become just second derivative of v with respect to x squared is zero. You all follow me what I've done there, right? Now, if I integrate both sides of this, well, here I'm going to get what? I'm going to get dv dx, right? And it would be equal to a constant, right? You agree, class? This is going to be a standard trick that doesn't matter what's over here. If you do an integration and it's with undefined limits, you have to put a constant on there. Do you all agree with this? The derivative of this will be zero. So del squared of x, or second derivative of v with respect to x squared will be zero. Now, that's the first derivative, and that happens to be minus e. Remember, e is equal to minus the gradient of v. Therefore, if I get dv dx, which is going to be the first derivative, then I have minus e. Does everybody understand how this comes about, by the way? It's because of this negative sign right there. All right. And this, the operation of the gradient operator is a vector, but it's only the first derivative of v. So this actually would be e, and now I have to give it some context. It would be in the actual z direction, but for now, you can leave it there. Then I take another integration of this, and now I get, when I go down here and take another integration, now I get v would be equal to cx plus, call it c1x plus c2. So I started with this differential equation right here, second derivative of v with respect to x squared equal to 0. And after two integrations, I get this. Now those constants are arbitrary, correct? And then you have to evaluate the constants. So if I say I put a voltage, for instance, if I put a voltage across this plate where, call this that z equals 0, this lower plate, this would be 0, and this would be d, and this would be the z direction. Then if I said the voltage here, v at the ground was equal to some v naught, and v at the upper plate was equal to 0, I'm just giving some context to it. I've got v0 here, and then I have 0 volts here. Then I'd have to solve this differential equation for the boundary values. And I know at 0, I have v0. So I put v0 equals to c1 times 0, which means c1 goes away, plus c2. So it means C2 would be actually V naught. And then I have the equation V is equal to C1x plus C2 or plus V naught. And I know this voltage would be 0 at, and I've got a function of X here. I'm sorry, this should be, really, this should be Z. Sorry about that. And this should be Z as well, because this is a function of the height of it. So if I've got C2 as V naught, then C1 here would be actually, if I looked at this, I know that 0 would be equal to C1 times the height or times D plus V naught, or C1 would be equal to minus V naught and divided by D. These are simple boundary value problems, and I'm over by a few minutes. Well, I got 9:17. Y'all follow me on this? So really, you're going to find the differential equation that describes the behavior of the voltage, solve for the boundary values to get the voltage between them. And then, well, I'm going to stop here. I'll let you do some problems with this stuff for homework, and we'll go ahead and we've got this chapter finished. We're going to start next time into magnetostatics in chapter 4. Okay. Everybody go to that. Now, anything to report for the good of the group or any questions before I go?
Professor, did you upload the capacitance homework on OneNote? Because I couldn't find anything,
Yeah,
like
I-
any problems on capacitance.
I'm going to tell you, I may have not, and I'm going to do that. All right. I'll give you the final set of problems from this chapter, boundary value and capacitance problems today. All right.
Okay.